Welcome to Study Loop.
Okay, problem 91 of chapter 17 from Thermodynamics and Engineering Approach 8th edition. Now, in this question, we are given the following upstream conditions: 70 kilopascals pressure, 260 Kelvin temperature, and the Mach number 2.4 initial. And we are told that there is a two-dimensional wedge of half angle 10 tilted at 25 degrees. So we have a wedge here making an angle of 25 degrees with the upstream flow, and we are also told that the half angle is 10. So the first thing that we want to find out in this case is always at what angle is the shock wave, at what angle is the downstream flow going to be, and that is parallel to the upper edge of the wedge. So you can clearly see that this angle is 25 minus 10 equals 15 degrees. So this angle is 15 degrees. We're going to use this in our calculations, and the question is, we want to find the downstream Mach number, the downstream pressure and temperature. So yeah, we're going to have shock waves in this direction, let's say, and we want to find what's happening on the other side of the shock wave. So again, this problem is very similar to one of the examples given in the book. Let me tell you that example number in 1 second. It is example 1712 of the book. So the situation is slightly different here, but we'll be using the same procedure. So I have mentioned it. I've mentioned it here for you. We are first going to calculate. We are going to use the Prandtl-Meyer equation. Prandtl-Meyer equation to solve. That equation is this: VMA equals root of k plus 1 by k minus. You can see it in this example over here. I won't write it down again because I won't write the whole equation down because it's just from that example. Tan inverse of I'll just write down the first term here, k minus 1 by k plus 1 and Mach square minus 1, and then there's a second term, and we have to solve this. Basically the k value for air is 1.4, the Mach value is given to us 2.4. so this can be easily solved using a calculator, and it is found to be equal, on solving this you find that the value is equal to 36.75. So once we have this, we use the other equation given to us for theta. Again, in example 1712, we're just following that procedure to reach the point where we'll be able to calculate the pressure. So we go by that equation, theta equals nu of Mach 2 minus nu of Mach 1, and yeah, we use this to calculate so we know these values to be 15 and 36.75. So this is equal to 51.75. So now that we have this, we basically need to use the isentropic equations to find P2 and T2. We only found the nu of Mach A2. First we need to find the Mach 2 from nu of Mach 2. So with this procedure, what we'll basically have found we'll have found the velocity of sound, so the velocity of airflow on the downstream side. So this is an implicit equation. There are two ways to find it. One is the expansion fan tables, and the other way to find it is to invert this Prandtl-Meyer equation by using Mathematica, MATLAB or such software. So either of these cases that you use for finding MA2 from nu of MA2, you find the value to be equal to 3.1. So once this is found, we use the isentropic equations, which are given again in that same example for the situation of pressure. P2 equals 1 plus K minus 1 by 2 Mach 2 square minus K by K plus 1, K minus 1. You can, I won't write the whole equation down, you can take it from that example from page number 875 of the book. And if you solve this, you get the pressure value to be equal to 23.8 kilopascals. And the temperature has a very similar formula, except for the exponent factor outside. So again, it's given by, I'll just write it down here, 1 plus Mach 1 square K minus 1 by 2 divided by 1 plus Mach 2 square K minus 1 by 2 times T1, of course. So when you solve this one, you get T2 equals 191 K.